Cristina Paredes, Executive Director for South Carolina Nexus.
Oh, that's
Good afternoon, everyone. Hello. I'm really excited to be here today and to be able to share this great conversation with our panelists today. You know, South Carolina is proud to be at the center of the national conversation around energy. SC Nexus is a federally designated tech hub and a part of the Division of Commerce. And we see energy as one of the greatest opportunities of our time. It's an opportunity to develop, test, and deploy technologies that strengthen our grid, advance national security, and drive economic growth. And you know, really, when you think about it, South Carolina's story is really America's story. How innovation, industry, and collaboration come together to shape our future, and in this case, the future of energy. And that cannot be more evident than through the conversations that are being held right here today at the South Carolina Nuclear Summit. And I just want to take the opportunity to thank the university, the Palmetto Nuclear Coalition, and Santee Cooper for bringing us all together to have this very important conversation about nuclear technologies and how our state plays a role in that. And now it is my pleasure to welcome our panelists to the stage. I would take a moment for each one of you to introduce yourselves and a little bit of your background.
Thank you. My name is Jeff Uphues, and I'm the CEO and president of DC Blox. We're a data center developer and operator that operates across the Southeast United States. We entered South Carolina in 2019 with our first data center that was a hyperscale-ready facility in Greenville. After that, we came into Myrtle Beach, South Carolina, and built the world's now largest cable landing station across the United States and on the eastern seaboard that literally connects two continents to export compute and resources to enable South Carolina to be connected to the world. From there, we built another long-haul fiber network, built a fiber network between Myrtle Beach back through 8 counties in South Carolina, connecting the data centers together, and then finished with another facility under construction right now in the North Augusta area. In total, DC Blox is a company that we have deployed about $2.4 billion in capital. We're currently deploying another $2.7 billion now. We have 14 data centers under development, and we employ about 700 people across all of our job sites that are in the Southeast and operating in 9 states.
Thank you, Jeff, and thank you for your commitment to South Carolina. Jonathan?
Jonathan Stevens. I'm a nuclear engineer with BWXT. BWXT manufactures all of the nuclear reactors for the U.S. Navy's submarines and aircraft carriers, so that is well over 400 reactors and counting, and several more being manufactured every year. So while you did hear this morning that only a couple of commercial reactors have been built this century, we've been dutifully making naval reactors without stopping for 6 or 7 decades. We also have a significant presence at the Savannah River site and doing environmental work. I'm down here from Lynchburg, Virginia, from our Advanced Technologies Group, where we are designing microreactors for defense and other purposes, ultimately to be commercialized as well. One of those, in light of the purpose of this particular panel, is Project Pele, which you heard referenced briefly in the last panel. Pele, we are building the prototype for that right now in Lynchburg, Virginia. You may have seen in the news that we just shipped all of the fuel, which has been completed manufacturing, to INL. The reactor itself, once that is completed, will also be shipped to INL, where the fuel will be loaded at that point, and we will start it up. That is the only microreactor currently under construction. It's a high-temperature gas reactor, TRISO fuel. You'll probably hear more about that later. It's 1 to 5 megawatts electric. We're limited into specifics we can give, although that is likely to change. We'll probably be able to open up a bit more on it in the near future. But that's just one of a number of reactors in terrestrial space. We're working on stuff for space. Commercial maritime is a very popular growing area in nuclear, so lots of excitement.
Thanks, Jonathan. Jim?
Yeah, I'm Jim Blankenhorn. I'm a senior vice president with Amentum, also a retired brigadier general. So Admiral, hate to say it, but go Army, beat Navy. Amentum is the largest nuclear company in the state of South Carolina, and arguably in the United States. We have a global presence in almost 80 countries. We're leading the nuclear resurgence internationally and are positioning and partnering to lead the nuclear resurgence here in the United States. We have a presence across South Carolina, both at Savannah River site, with the fuel fabrication facilities, with the Department of Defense facilities here in the state. We also have a presence at most of the Department of Energy nuclear facilities and sites across the United States, including national labs. So we support Savannah River National Lab here in South Carolina, but we're also a member of the Idaho National Lab team, Los Alamos, Lawrence Livermore, and several other national labs. The significance there was the Idaho National Lab, which is where Project Pele is being demoed. But it's the nation's nuclear research laboratory for nuclear reactors. They've tested and started up over 51 reactors at that site in its history. But today, they are the nation's test bed for microreactors through their dome facility and a couple of other facilities that they've designed and have made available to industry to showcase and demonstrate and test microreactors in anticipation of deployment and accelerating that deployment. So,
thanks, Jim. Glad to have you here today. Jordan?
Hi, all. I'm Jordan Bramble, CEO of Antares. We focus on microreactors for defense and space applications. We have a presence in Aiken, South Carolina, just outside of the Savannah River site. We have some partnerships with the University of South Carolina that we're very excited about. And in addition to the state of South Carolina, we have facilities in Idaho Falls, just outside of Idaho National Lab, as well as 145,000 square feet of manufacturing space in Torrance, California. We're really excited about some of the long-term prospects for development and manufacturing in the state of South Carolina. Touching on our DoD focus a little bit further. So, the other panelists actually gave a great lead up to what I'm about to say. We are also working on a microreactor testbed at Idaho National Lab. We're actually working with BWXT on fabricating the fuel as we speak for the first 2 core loads. So while we haven't really announced it publicly, we are at least one other microreactor that actually is now in construction. We're in PDSA phase, preliminary documented safety analysis, with the Department of Energy, and we'll be sharing more on that publicly soon. Just really excited to be here today and, talk more about what we see as the long-term prospects of the state.
Thanks, Jordan, for joining our conversation today. And Admiral?
Absolutely. So I'm Paul Gaffney. I'm honored and flattered to be here with the 4Js at this, and with you, Cristina. Thank you very much. So the commonality between a cadet from West Point and a midshipman from the Naval Academy is they were both accepted at West Point. So I'm I had 39 years of service in your United States Navy. Ran a university, 2 universities for 13 years, and I retired here. Chose to come to Columbia, South Carolina, to work for and be an advocate for the College of Engineering and Computing. And I think I'm here partly to give a defense perspective, even though I'm not currently employed by the Department of Defense. But of course, very proud, Jim, you mentioned it, half of the nuclear reactors in America today are owned and operated by the United States Navy. So we have a certain perspective. I think that interests many of you, and very interested in both base installation reactors, small modular reactors, or microreactors for bases, for installations. There are about 450 to 500 bases in the United States. And for forward operating bases where which we've just seen in recent conflicts, there were 505 in Iraq, for example. So this is a big market if we can get going. Thank you.
Thanks, Admiral, for joining us today. And you're absolutely right. The purpose of our panel conversation today is to focus on nuclear power for national defense and where that comes from: SMRs, microreactors, and mission readiness. Kind of building off of your opening, Admiral, from your national security vantage point, why is this the moment in that the U.S. must move aggressively on microreactors and SMRs for defense installations?
Well, I guess there's two reasons. Well, first of all, there was another moment about 10 years ago in 2016 where we recognized that we needed to have small reactors in the field to support our folks, because for every 1 gallon of fuel delivered to a soldier or 1 gallon of water delivered to a soldier, you spent 7 gallons of fuel. And during that trip, there were many casualties and severe injuries, and we need to stop that. We're in a bit of a lull now, but nonetheless, still needed, will be needed in the future. But there is a threat. We heard today that the grid is at capacity. There's going to be more and more and more pressure on it. And then we have unfriendly people that can easily come in and disrupt that. So for our installations, we need to start to build security and resilience. That's the threat. The opportunity is, and let me actually read this. This is the President of the United States a couple of days ago. We want a resilient national infrastructure that can resist and thwart foreign threats. No adversary or danger should be able to hold America at risk. That tells me there's a priority. The President has said it. On Sunday, the National Defense Authorization Act was exposed. It's not been voted on yet, but both the House and the Senate have, in many places, in many different sections of those proposed bills, have talked about portable reactors for forward operating bases, and also secure, resilient energy based on nuclear power on our installations in the United States. So we have both an opportunity. Everyone's lined up. The governor's lined up. You're all lined up. The House and the Senate are lined up, and the President's giving us the go signal.
Yeah, I'll build on that. The comment about casualties during fuel supply, that was definitely a big driver of Pele. And in fact, early in the project, we used to have a graphic we would put up where we would show the reactor, the footprint of it, which again fits in a 20-foot shipping container, very small. And then the field of diesel trucks that it took to supply the equivalent amount of energy from fuel deliveries. And it was really a shocking image to look at. With Pele, even beyond that, there's also this idea of, if you're talking forward operating bases in particular, the fact that it needs to be easily movable. which is a big haul for a nuclear reactor. Most of the ones you're aware of, even after you've stopped operating, the fuel really can't go anywhere for a long period of time. And so we've had to deal with the challenge with Pele of being able to set it up very rapidly, operate it, shut it down, pack it up, move it to another site, either by a truck or a aircraft, and redeploy it. And so one of the interesting things I think will be a lot of fun to see at INL, because it is meant to be field deployed, the prototype will be field deployed, as though it were a real scenario. It won't be in any of the indoor facilities or anything like that. So that will be, we're very much excited to seeing how that goes.
Jordan, did you want to add something?
Well, we love the idea of mobile reactors. We love the idea of installation resilience. We almost think of it like a spectrum. So there's a lot in between that as well. And I think something else that would be worth hitting on, going back to the idea of a resilient national defense architecture. As a country, we are investing in missile defense again. And it's something, frankly, we should have been investing significantly in over the last few decades. But it looks like we're going to embark on something like $100 billion in expenditure on new missile defense infrastructure over the coming decade. And there's a national imperative to do so. At the end of the Cold War, we kind of assumed that mutually assured destruction was a thing, and the status quo was just going to remain as such. And we now live in a world where the strategic calculus is it's now multipolar. We have adversaries that have made exceptional progress on hypersonic strike capabilities and hypersonic glide vehicles. We have an adversary in Russia that's openly developing technologies that undermine the concept of mutually assured destruction. And so the only way I see to really counteract that is to develop next generation missile defense technologies, deploy it at continental scale, and we will have to bake resilience into that from the very beginning. So when we think about, where is the greatest capability unlocked for micronuclear, a lot of these are operational assets that actually exist on installations. And so the lines between operational energy and installation energy are starting to blur. And it's not just the interceptor sites themselves, it's the radar, it's the command and control, it's the communications, it's how we communicate with our assets up in space and how we bring that entire architecture together. It's all dependent on power. A lot of the sites where these systems would be deployed are in places where power is scarce right now, whether that's the North Slope of Alaska or islands in the Pacific. And that's a role that nuclear energy can really fill like no other.
It's, listening to you answer that question, Jordan, brought up another one for the panel here. Building off of your answer, how does nuclear power strengthen mission assurance during grid outages, natural disasters, or adversarial attacks?
Well, it's a great point, and I'll anchor it back to missile defense and strategic deterrence again. If when we developed a lot of this stuff for the first time, we really started in the 70s. The internet didn't exist. We didn't have an adversary that could bring down the commercial grid with a cyber attack. Those were never things that we had to plan for in terms of operational readiness. Well, we do now live in a world where we have an adversary that has demonstrated the ability to bring the civilian grid down. The way that we train, the way that we equip, the way that we deploy, even the actions we take on homeland defense to deter an attack in the first place, it all starts right here in the homeland, and we need to be able to power it. The status quo right now for how we do that is we put fuel in diesel generators. And the challenge for that is, that fuel goes bad, especially in harsh environments. We have to swap it to maintain it. And in the worst case scenario, our military could be at odds with the civilian sector. Fuel that could otherwise go to civilian hospitals will have to be on military basis to sustain. And that's the huge positive of nuclear energy. You can break yourself from that logistics vulnerability and potentially operate for years without the need to refuel. The other thing is, unlike renewables, which have low capacity factors, military operations are 24/7, 365. You need to be able to sustain when the sun isn't shining, when the wind's not blowing, when a liquid fossil fuel supply chain doesn't exist. And nuclear energy is really the only technology that can get you that can get you those high capacity factors. We think a lot about the architectures where you can put microreactors together modularly so that you can overbuild a little bit and really could get to 99.9% uptime and the kind of high capacity factor that the military is looking for.
Jeff, Sorry, go ahead.
I was going to say another aspect to the resiliency story is this idea with microreactors. It opens up the possibility of more distributed power. So, for example, a year or two ago, I was in Alaska talking to folks who run the grid there. And one of their biggest worries is, in some cases, you have transmission lines that go hundreds of miles from a central power plant, or you may be running a gas plant and the gas only has a single gas supply line to it that runs for hundreds of miles. If you can distribute these smaller reactors into other locations, especially local locations that don't need the amount of energy in, say, an AP1000, there's a resiliency story there to tell, even outside of defense specifically.
Yeah, and that's a really great point. There's a lot of talk about how expensive it is to build a nuclear right now. The schedule is how long it takes, but go look at what it's taking some states to build 100 miles of transmission, how long that takes and how expensive that is.
Jeff, kind of the same question for you about mission assurance. I know when I can't get access to my data because of grid outages, that's mission assurance for me. And I'm sure for many people here in the room, from your standpoint, how do you see nuclear power as that mission assurance during grid outages and, adversarial attacks too?
Yeah, well, first and foremost, every single person in this room that is holding a phone in their hand is connected to a data center. When you think of the cloud and you think of infrastructure and the things of what we have, a data center or access into the cloud is really four walls, and it's called a data center. And a data center needs connectivity, because without connectivity, it's on an island. And without power, it will not power any of the things that you've come to be relying upon, whether it is your day-to-day applications, how you run your home, and especially around AI computing and everything for what we are doing. So, the critical nature of nuclear power, when you look at what we do, we're an off-taker, as well as when we serve large-scale hyperscalers, which that is a majority of our business and where we put our facilities. We're always looking for access to the grid. It makes it very difficult in site selection and where those things go. So if it's difficulty in trying to find the next site because we're trying to intersect where the grid is available, where transmission is available, where the opportunity is, say, can you get gas to these facilities that you could provide behind the meter solutions or some type of LNG. These are very, very, very difficult things to source, which starts to look a little bit like a needle in a haystack of where is the most effective place to put these. The true way to get these data centers and win the AI race is constant, always-on nuclear energy and putting that into places that is both publicly acceptable, because I think more and more what we have to do is educating much of every American of the benefits and the safety of what nuclear energy is, because I think that there's been a lot of things through the last few decades that have said, oh my gosh, I'm worried about this, whether it's a Chernobyl or it's a 3 Mile Island. We have to do a much better job as a society of educating the reliability, the constant always-on energy, the availability, and the safety of what this is. And that is going to be the only way. We can't build gas fast enough. We can't build, more electrical grid and transmission fast enough. We are going to have to rely on nuclear if we want to win this AI race and if we want to continually powering our country for the next 200 years.
You bring up a good point about safety and education and kind of leaning on site readiness, if you will. Jim, if you could, from your perspective, what are some of those real world deployment considerations when placing a microreactor or SMR, whether it's on a military site or co-located next to a data center, from construction, permitting, security, and training? If you could just kind of give us your insight there.
Sure, thank you. Yeah, the justification of need for power to support Department of Defense military operations, whether it's CONUS or whether it's deployed forward and forward operating bases, is well defined, and the panel has done a great job of highlighting the vulnerability of our systems, the dependency on power as a national and as a international center of gravity, and the importance of reliable survivability, power, continuity of operations So I think the panel's done a great job defining that. Now, when we now switch to execution, earlier panels talked about a number of deployment challenges for new nuclear, and I think we're going to see similar challenges for deployment of SMRs and microreactors on military installations. So we're going to see the same types of challenges in terms of licensing and regulatory, supply chain, fuel. We're going to see the same workforce and resourcing challenges. And then specifically with the microreactors and the SMRs, we're going to see this added pace for technical maturity as a challenge. And then when you probably the additional deployment challenge for military installation is going to be on top of all of that will be the heightened security aspects. The training will be the same, the qualifications will be the same, but from a security perspective, there will be additional both personnel and facility security requirements that not just the people and the materials will have to meet, but then also the long-term survivability of these systems. So whether they are a fixed asset or whether they're a mobile asset, obviously the bottom line is the justification of need is that we have reliable power on demand 24/7, and that then implies that is an asset now that has to be protected. So there will be survivability design attributes that will have to be factored in, different perhaps than what you would find in a commercial off of a federal facility deployment.
So mentioned a lot in your comments and Jeff's comments was safety considerations. And so, Jonathan, I wanted to, kind of ask you in your perspective there, how are you seeing advances in core design and fuel innovation improving safety and mobility and performance, especially when we're talking about defense microreactors?
Yeah, sure. Yeah, so a lot of these reactors, technologies for microreactors, what we call, you might have heard Gen 4 technologies. They're usually characterized by advanced fuels, advanced moderators. I hesitate to use the term safer because it implies, I think some people interpret that as meaning that the big commercial reactor PWRs out there are not safe, which is not true. They are very safe, but they're safe in a different way, these Gen 4 reactors, given some of the operating profiles we're looking at, like what if somebody shoots a missile at your base or something like that, right? At the end of the day, the safety comes down to making sure we don't release fission products to the environment. And these advanced technologies do that there's a few different ways you can manage that. One is to use a reactor that doesn't operate under any pressure. One is to use something like TRISO fuel, which is what most of our designs do, and a number of designs out there use this TRISO fuel, which the 20-second description of that is you can imagine little kernels of uranium size of a poppy seed with several layers of ceramic coatings around them. And what that affords us as an advantage over, say, traditional metallic clad fuel is you can design reactors that can never get hot enough under any accident scenario that it would exceed the melting point of the fuel. And so some people call them walk-away safe reactors, even though you wouldn't really walk away from them. But they lend themselves particularly well to these applications where you've got maybe additional security concerns or a lot of mobility, so you don't have the ability to put in many feet of concrete around your reactor. So that's really where those fuels where those shine. There's a lot of most people are looking at what we call HALEU enrichments. That's the enriched to anything up to 20% enriched U-235 fuel. That's allowing for along with these advanced forms, is allowing for longer fuel cycles, advantages like that. But yeah, that's, I guess one last thing I should mention is that, of course, a lot of the technologies out there were originally designed 60 or 70 years ago, and clearly our tools have come a long way since then. Computer models, things like that, and it can be a double-edged sword because I've seen a lot of computer models that are completely impractical from, say, a manufacturing standpoint. But nevertheless, we have a lot of advanced tools out there to make our jobs easier. So that's just a few examples.
You anticipated where I was going with my next question. You mentioned Gen 4 and newer technologies. So Jordan, would you talk to us a little bit more about what distinguishes today's microreactor technologies from earlier generation concepts, particularly in like portability and modularity?
Absolutely. And he just hit on quite a bit of it. It's really high assay, low enriched uranium. So the ability to fuel these reactors at the HALEU assay. And then the advent of TRISO fuel. And, I would maybe abstract that a little bit and just say coated particle fuels broadly and what that's going to enable both for Earth and space applications. I think, something I would highlight on top of, both the safety case and the qualification that exists there is, we're a customer of BWXT. They've been a wonderful partner to us. We've been able to build on the back of this supply chain that was really funded by the Pele program, right? To the tune of perhaps tens of millions of dollars going into that fuel line. The reason BWXT could do that and get that up and running so fast was because the Department of Energy previously, over the course of decades, spent hundreds of millions of dollars on the AGR program, going and getting that safety data that made this fuel something that you could qualify and argue your safety case against. And so there's a lot new in nuclear right now. But it's all been built on, iterative decades worth of work to get to this point. And I think, if we continue to apply that iterative R&D, continue to invest heavily in these things, where we could be in the 2030s could be, a world where, we're moving beyond UCO TRISO to, uranium nitride TRISO, and we're able to get the uranium density in these systems up pretty significantly. Many of us, I think, are working on designs right now that are somewhere between 3 to 6 effective full power years of operation. I really think if we continue the R&D efforts, there's a world where we're going to be able to get these things to 12 plus years of operation. And there's another just sort of great piece of history there. And if you look at what the Navy did, they first developed the water-cooled reactor on the Seawolf, and they never stopped innovating iteratively, and they've continued that for decades. Now we don't even refuel the submarines because they go for 30 plus years. Microreactors could get to a similar point if we have the willpower to continue to invest in these things for decades to come.
So what type of military installations stand to benefit the most from these microreactors?
Yeah, and I think I touched on quite a bit of it earlier. We're really excited about future, next generation missile defense architectures. But beyond that, it's where we're operating our radar sites. We have command and control hubs on our installations throughout the country today that are responsible for commanding and controlling operations on the other side of the world. And, we need connectivity at all times. We have assets deployed here in the United States that are responsible for monitoring at high resolution what other people are doing in space in real time. And those need resilient power. Oftentimes, it's not even just the power. It's also the ability to produce heat or the ability to cool operational systems. And, when you look at these profiles, the beautiful thing about nuclear energy is you have both waste heat and you have electricity that's being produced. And at a lot of installations today, we're actually making electricity to then go generate the heat. And if you have the ability to capture both, you can build smaller scale systems, you can build them more cost effectively, and the economic case improves quite a bit.
Does anybody else want to?
I mean, the short answer to where would they best fit, it would be anywhere where you don't have reliable access to grid scale power. So most of these microreactors per megawatt are certainly going to cost more than what you would get out of a very, very large reactor. But if you can build them in a factory and send them to extremely remote locations, something that's very mobile could be used for catastrophe relief, things like that. That's really where they excel.
Yeah, I think to put maybe a little finer tip on it. So, when you talk about where SMRs or microreactors could best be utilized, I mean, there's obviously two different scenarios. You've got your fixed base, CONUS base facilities and installations, and then you have deployments. And so when you look at CONUS based fixed systems, you're really not talking about powering bases. What you're talking about is powering critical infrastructure on those bases that are required to operate 24/7 without interruption, because that is the vulnerability, that is the risk. If a threat bad actor can interrupt our continuity of operations, then they put our warfighters at risk. And so when you break that down a little bit, so what are you talking about? We're talking about command and control centers. Okay. We're talking about key communication centers. We're talking about lines of communications, lines of logistics, seaports, airports of entry and debarkation. And then when you talk about, deployable systems, you're talking about forward operating bases, you're talking about beachheads, those types of systems that, quite frankly, are required and required to be mobile. And so, again, I think there's two different ways to look at that. But in terms of the critical infrastructures, at the bottom line, it's that which is needed to operate continuously without interruption. And it applies not just to military. I mean, you then can apply that nationally to the critical infrastructure that's necessary to keep the United States running economically and industrially, whether that's power systems or whether that's industry based or water systems or lines of communications, lines of transportation, et cetera.
Listening to the three of your answer, you can really see why the DoD is accelerating their interest in deployable nuclear power. I really would like to shift the conversation a little bit as we kind of near the end of the conversation today to focus on regulatory pathways and partnerships on that end. So can you kind of talk to us, and Jeff, we'll start with you and then kind of move down to the military side of things. What level of interagency coordination is required to deploy these systems at scale?
Yeah, well, I think that as we've been putting more and more emphasis around our government practice, and we first got into this when building our one of our data centers in Huntsville, Alabama, that is highly military, just right outside Redstone. And you look and see the interdependence on agency to agency to agency and how they're all interconnected. The sharing of information or the access to information. So I'll take it back one step. Here in South Carolina with our cable landing station, and when we integrated the capability there, that is of national security interest because of the types of data that comes in through that facility into South Carolina globally. That is also connected back through our fiber network that ties at major points of interest, like our fiber network runs around SRS. So when you start integrating this and you say, what is the national integration that needs to happen around data? You really need to have a holistic view and how data can either be shared and or how data, especially in AI, is integrated. So if you think of Myrtle Beach into SRS, into Fort Gordon, into critical assets in the Southeast and other places. This is everywhere around our country. And I think that as we continue to keep thinking about how do we provide agencies and other type that critical infrastructure, everyone is trying to deploy AI in some different fashion, and each one's got different standards in how they're trying to do it. And systematically looking at trying to align some of those interests. We see a lot of it with some of the hyperscale customers that we deal with that are all providing services and AI back to government entities. And each one is a little different, both the agency as well as the the hyperscaler that's deploying that in different technologies. So I think just more and more, I think it's becoming, we need more standards around that.
Admiral, what do you think about what we need for better interagency cooperation?
Yeah, well, certainly the DOE is going to have to be involved in this. And we have to also consider the sensitivities of every congressional committee that has some oversight over the agencies and of nuclear energy. That always complicates decision-making in Washington. But and what I understand is the Department of Homeland Security is now becoming quite interested, especially in the deployable mobile sites for disasters. In my opinion, the big game in town is still going to be the Defense Department. And the Congress has been asking, for example, for there to be a program of record to formalize it, and maybe a single leadership, an executive agent is the term they use. Because if you look at it right now, you've got Pele is SCO funded. You've got Janus is an Army program with DIU. ANPI is with DIU. You've got the whole Navy thing going. There's a lot. That's good news. There are a lot of people interested, but I think bringing it together so it is deliberately coordinated has not been done yet and needs to be done.
Okay. So, I mentioned that I wanted to make sure we touch on private-public partnerships. And when you look at South Carolina, we've heard several times throughout the day about how we are well positioned and we have a strong workforce and supply chain. And we know that many states want to participate in this defense nuclear innovation. But looking at South Carolina and things that we've heard today from different panelists, and from your perspective, what makes us well positioned when you look at workforce, supply chain, or national labs to support the defense and microreactor deployment?
Yeah, this one to me is I'm surprised I haven't heard more of this today about South Carolina in particular. And I'll preface this by saying there are a lot of states that want to take that role, that want to be the leader in this area, and microreactors in general. A lot of the action is in Idaho, Wyoming, Utah, areas like that. They'll all claim they've got great supply chain, they've got great people, all that stuff. So what is different about South Carolina? And to me, the first thing that comes to mind is none of those other states I mentioned are real close to the water. And we know that not only does the federal government have we have these executive orders on nuclear, but there are also orders out there about bringing back maritime. And maritime nuclear is, in my observation, one of the fastest growing areas of interest out there right now, defense or otherwise. And to me, it would seem like a logical collaboration would be with the maritime industry, the shipyards, the ports, Savannah River being one of the few federal labs that's accessible by water. That there is a real opportunity there in the field of commercial nuclear propulsion or floating nuclear power plants.
That's come up a lot in my conversations with Amentum there too. Jim, do you have anything like to add with that?
Yeah, let me answer your earlier question first. I think the governor, it starts at the top, and I think the governor hit it right on the head. When he started off today telling us, South Carolina's business is business. So when you look at South Carolina has, very favorable fiscal responsibilities. They have very favorable legislation. They're pro-technical. They're pro-nuclear. And then, South Carolina is the number one state in terms of the nuclear assets that they have, from national laboratory to nuclear operations to nuclear engineering to fuel enrichment and fabrication. We have nuclear reactors, and then put on top of that and it was mentioned several times earlier. We have this technical college system that's the envy of many places around the United States, but very focused on developing skilled workers for the nuclear environment and nuclear market. So I just think there's all kinds of reasons why South Carolina is best suited and best positioned to support the. And I wouldn't limit it to just defense microreactors. I mean, I think the state of South Carolina is best suited for supporting new nuclear in general, whether that's microreactors, SMRs, or gigawatt reactor deployments. So, looking specifically at microreactors, again, we have outstanding assets within the state. Both, number one, we have needs. So we have facilities that have needs for microreactor technology, Department of Defense, as well as critical infrastructure. And then when you move towards one of our greater assets, meaning our coastline, then we also bring in the nuclear fleet, which is, people are sort of mulling that over. But, I think that's the way of the future. I think the major ships are going to be nuclear powered at some point in time. And I'm not talking ship to shore power. I'm talking nuclear powered ships. And so, we're running some of the largest ports on the East Coast in South Carolina. And I think that's a great advancement and technology advancement for that port going forward.
Okay, we got 1 minute left. Time flew by really fast. I got one last lightning round question quickly for you. So kind of building off my last question, what must South Carolina do in the next 2 years to ensure our state is ready? We've heard a lot about VC Summer and the AP1000s, but when you look at SMRs and microreactors, what do we need to ensure that we're ready to continue to court new companies and new innovation in this area?
Dream big, execute well, and educate and empower the people of South Carolina.
Yeah, I would agree that, and we heard this in previous panels, that executing on projects really is a big one. And to elaborate on that a tiny bit, you may wonder, why is it we're not building SMRs like crazy already? Why is it not happening now? We've had the technology for a while. And I agree with what I heard earlier this morning, that it is not because of regulatory issues. I think the NRC is moving in the right direction in that area. What it is I think it is concerns from potential customers that will be a problem, or that other things will be a problem because the nuclear industry doesn't have a great record of delivering on time and on budget. So there are a lot of people waiting on the sidelines to see some things work the way we said they were going to work before they jump in and really commit.
Thank you.
Be bold, stay the course.
I like that.
I think stay focused and exploit the advantages that you already have. In addition to the workforce that's here for nuclear already, there's a great automotive and defense manufacturing workforce here with transferable skills right into the nuclear industry, especially with things like microreactors as you think about power electronics. Really invest in the great university system you already have. We're really excited about our partnership with the University of South Carolina. In fact, as part of their Nuclear Innovation Center, we're making a contribution that's going to exceed $1 million in an electrically heated demonstration prototype to get the students involved with it. And, when we consider our larger in-kind contributions, it'll be quite a bit more than that. So we just need to stay focused on developing this workforce and, using the advantages that the state has. I'd also highlight the Savannah River National Lab, great capabilities in the back half of the nuclear fuel supply chain, access to the water, can be a great asset to partner with the Defense Department as it seeks to deploy microreactors across its installations.
Jordan, it's great to hear about your collaboration with the university. Thank you so much for your support. I know that goes a long way in building our workforce here. So thank you for that.
Thank you.
Admiral?
We're going to deal with the federal government. That's a contact sport. You've got a great team here, led by the governor. We've got the perfect congressional delegation, industry and academia coming together. One team, contact sport, get the job done.
Well, thank you so much for joining us today. Let's give a round of applause for our panelists. And you heard it from them. We got to dream big and execute well.
Thank you, Vito. That's wonderful.